And a big welcome to Bob. Thanks a lot for coming all the way here from Tralee. Just a quick intro. I don't think there's any introduction for Bob because everyone knows who he is, surely. So just a quick thanks to our sponsors from DCare and Newsweaver for sponsoring the event. And basically, if you want to follow us, we're on Twitter and LinkedIn. And I'm just going to hand straight over to you because... straight over.
Well, thank you for inviting me. It's always fun to do these things. So, I'm Bob.
Hi, Bob.
Okay, so I have my laser. And it took a long time for people to develop a green laser. Red lasers were easy because the band gap in silicon is such that you can dope it and get red out of it pretty easy. In fact, when I was a kid, my buddy and I bought a whole bunch of diodes from an old surplus catalog. We got a couple of hundred diodes. The diodes were little glass things that had wires going into them and a little cat's whisker wire inside that touched a little blob of silicon, and that was a nice silicon diode. And of course, we didn't know if they worked. So I set up a little rig in my basement. It was a block of wood with 2 nails in it that went to a train transformer that was a DC transformer and to a light. And then what I would do is I would take each diode, I'd put it on the 2 nails, and then I'd turn it around. And it should conduct in one direction and light the light, and it should not conduct in the other direction, and the light wouldn't light. So I went through all the diodes, going ding, ding, and then I'd put them into piles. Some of them worked, some of them didn't. Some of them would flash the light. The light would sit there and go, ooh, I put them in a special little place. But the most interesting diodes, and there were only 3 or 4 of them in this whole batch, worked just fine, except that when you put them on the nails and they worked, they also lit up. They lit up with an orange light. What the heck? You know, I'm a kid. I was like 12 or 13 years old. What the devil is going on here? Diodes aren't supposed to light up. It turns out that back in those days, they didn't have a lot of good control over the impurities that they were putting in the silicon. So every once in a while, they would get the impurities just wrong enough to get the band gap so that it would emit light. They had light-emitting diodes. They just didn't know what the heck they were doing back then. So they had these light-emitting diodes, and okay, fine. So anyway, this is a light-emitting diode that emits green light. Took a long time to figure out how to do green light. Blue light's even harder, but we're not going to go there because I have something else to tell you. Now, this green light, this is a laser diode, which is really just a light-emitting diode where they polish the surfaces so that you get reflection inside. And okay, so my laser diode, fine. I've got a. This is my grandchildren got this for watching fireworks. These are diffraction gratings, right? Little transparent bits of plastic with lines drawn on them. 13,500 per inch. I don't know what that is per centimeter, but okay, right? You guys are Irish, you know what inches are. So, if I run my laser through that, I get this. Now try to explain that.
Interference.
It is, it's interference, and that's an interference pattern, right? So I run my laser through it, and look at that. There's a tremendous amount of dots on the screen, and it would be very easy to suppose that the dots are actually infinite, that they continue on in an infinite pattern, getting dimmer and dimmer and dimmer out to the extent, and that is in fact what happens. This pattern does not end. Notice that in the center it's very bright, and then the 8 dots around that are pretty bright, and then the many dots around that are sort of bright, and so on and so on and so on. Okay, so now let's do a thought experiment. I'm going to take my laser here, and I've got a little imaginary knob. I'm going to turn that knob down so that the laser gets dimmer and dimmer and dimmer. I'm going to get it so dim that it's firing 1 photon per second. And I'm going to then take my 1 photon per second, there it is, 1 photon per second. We will imagine that you can see 1 photon. There's my 1 photon per second, and I will now take the 1 photon per second, and I will pass that photon per second through the diffraction grating. And what will you see when I do that?
I know.
Now, a photon must deposit its energy at one physical location. So you will not see, by definition, you will not see that. You must see individual dots. What would you see?
You'll probably see the center dot.
You'll probably
See the center dot.
see the center dot.
Probably.
Anybody else want to take a guess?
You see the center dot more often than the other dots.
You would see the center dot more often than the other dots, but you would see the other dots. And if you measured the intensity of those dots and turned that number into a probability, then the probability of seeing the dots out here would exactly match the intensity that you see here. Now, what's going on here? First of all, why this interference pattern? What's going on? Well, we know what an interference pattern is. An interference pattern is when some waves pass through slits and they go into little wavelets, and then the wavelets all interfere with each other with construction and destructive interference, and they create this lovely pattern. This is a standard pattern. You can make this pattern with water. You can do this with water waves. Has anybody been to an amusement park where they have a wave tank? Anybody been to one of those? You've been to one of those. Okay, so big wave tank. What they've got is this massive pool full of water, and then at the back end they've got a big reciprocal pump. And the reciprocal pump is pushing with these 2 pistons. And the 2 pistons create 2 sets of waves that interfere inside the tank and create all this wavy stuff. But if you look on the back wall, right where the waves are being generated, you'll see this lovely standing wave interference pattern. Anyway, you can do all of this with water. You can do it with light. This is one of the proofs that light is made of waves. The problem now is that when I take and I fire 1 photon per second and I get this, but the dot in the middle is more often than the dots around the outside, which are more often than the dots around the far outside, the position of the photon matches the probability of that amplitude. If you were to take a camera, open the shutter, and leave the shutter open for an hour, collect 3,600 dots, and then develop the film, that's what you would see. There is no algorithm that will tell you where a particular photon will land. It's as random can be. It matches the best random test we've got. This experiment's been done like 1 trillion times, right? Because all the physicists go, we don't understand this. We have to do it again and again and again. And they do it over and over, and they look at it and go, you don't understand what's going on. Nobody understands what's going on. But what it implies is this. 1 photon passes through the diffraction grating, breaks up into a bunch of wavelets. Those wavelets from the single photon interfere with each other and put an interference pattern on the screen. Not an interference pattern of light, but an interference pattern of probability. And then the photon decides, using that map of probabilities, where to deposit its energy. And it does so utterly randomly, just with that probability map. Which means that the interference pattern is an interference pattern of probability, not an interference pattern of light waves. There's no such thing as light waves. There are probability waves. A photon is the energy at a location that is deposited by a wave of probabilities. I'm not going to talk about that anymore because no one understands this and it makes my head hurt. So we're going to talk about something I do understand, which is architecture, software. This is a talk that I've given many, many times over the last 6 or 7 years. And it goes back in time to a moment where my son was showing me an application that he was in the middle of writing. And I can give you a small demonstration of it. What he showed me was this. Any Ruby programmers here? Oh yeah, Ruby, you're one guy. So, now, in the United States, Ruby is a very hot topic. All the social networking companies have decided that they can get to market faster if they use Ruby. So in the United States, if you are a Ruby programmer, for all intents and purposes, you can write a number on a piece of paper and find somebody to pay you that number, and it doesn't much matter what the number is. I have seen companies purchased for many millions of dollars for the sole purpose of getting the Ruby programmers inside that company. They throw away the business model, they tell the customers to go to hell, and they take all the Ruby programmers and they recommission them, and they would pay about $1 million per programmer just to get them. That's a bubble, an economic bubble. I'm sure it's going to break, although I've been saying that for the last 5 years. Anyway, if you want to earn more money, learn Ruby and move to the United States. I don't know how long that bubble will last, but here's my son. My son presented a directory structure to me that looked like this, and he was asking me to review his code. And I looked at it, and I noticed something. Now, you're a Ruby programmer, you know that one of the big frameworks in Ruby is Rails. Rails is the master framework. Everybody uses Ruby on Rails, blah, blah, blah. Okay. If you're doing Ruby on Rails, the high-level directory structure looks like this. So when my son handed this to me and said, "Dad, would you look over my system?" and I saw the high-level directory structure, I said, "Oh, this is a Rails application." I can tell that just because of the directory structure. And then it hit me. At that moment, it hit me. I said, wait a minute. Why is it that when I'm looking at the top-level directory structure, I know it's a Rails application, I know what framework he's using, I don't know what the application does? Why don't I know what the application does? Why isn't the top-level directory structure telling me what the application does? Why is the framework superseding the intent of the application? And that bothered me. I thought about it for a while, and I thought, now wait a minute. I'd seen many web applications before, and I'd seen many Ruby applications before. It hadn't bothered me before. It was just this one day, probably because it was my son, and when it's your son, you must be hypercritical. I thought about it, and I said, wait a minute now. Ruby on Rails. Rails is a web framework. Now, what's the web? Web is an I/O device. You might think, no, the web is some hyper-important architectural element. No, it's not. It's an I/O device. You get your input from the web, you send your output to the web. The web is an I/O device. And one thing that we have learned over the last 50 years is that you abstract away your I/O devices from your application. You don't let your application know what your I/O devices are. We learned that back in the 60s. You know, big IBM systems. You'd have big, massive systems that had tape drives and punch card readers and punch card punchers and line printers, and someone would say to you, "I need a payroll application." And you'd say, "Okay, well, where's the data coming in from?" "Well, it's going to be on this big deck of punch cards." "Well, where do you want the data going out to?" "Well, I want you to punch another deck of cards." And so we'd write this code in assembly language that would read in from the card reader and do all the math and write out to the card punch. And no sooner had you done that and got it all working that the customer says, "That's too slow. We need it to come in on the tape drive. We're going to move all those records over to the tape drive, and we want you to read from the tape and write to the punch." And you've got to rewrite your program. Because now all of a sudden you're using a completely different device, and the code you wrote was hardwired to the card reader, and now you've got to redo the whole thing. And after a couple of those, somebody got real smart and said, we probably shouldn't know what I/O device we're using. And so the whole notion of device independence was created. And that was created a long time ago, way back in the IBM 360 days, the DOS operating system, device independent. OS operating system, device independent. Unix operating system, device independent. One of the big early abstractions that we invented back in those days. So here I am looking at this going, why is this yelling at me about its I/O device? Because the web is just a delivery mechanism. It's just an I/O device. Why should the top-level structure of this application be yelling at me about the I/O device? So I did a little research. And I knew what I was looking for. I went looking for blueprints. And I found some blueprints. This is one. And I thought, now here's what an architect would draw, a building architect. And this is a depiction of a library. You can tell it's a library because it's got the word library on there. But other than that, you can tell it's a library because it looks like a library. You've got bookshelves here and computer terminals there and the tables sitting there and there's a circulation desk and so on. Looks like a library. And if that doesn't convince you, this one will. That's a church. And it just yells at you, I am a church. Now what it doesn't yell at you is, I'm made of wood. The framework is not evident here. The building materials, the structural elements, those are not visible there. What this is yelling at us is the intent of the building. And it occurred to me that architecture is always about intent. And that's what was bothering me about my son's application. It wasn't telling me what it was intended for. That high-level directory structure was telling me something I didn't want to know. I didn't want to know it was a Rails app. I wanted to know what the application does. And that's when my memory got jogged, because this is not a new issue. This is an old issue. And I remembered a book that I had read back in 1992, which talked about this topic. And it was this book. Some of you may have read this book in your past, and some of you may know who this guy is. The guy's name is Ivar Jakobsen. And if that name doesn't ring a bell, well, let me remind you of who Ivar Jakobsen is. Back in the 90s, you may recall that there was a company called Rational, and Rational had a chief scientist. The chief scientist's name was Grady Booch. Anybody remember that name? No. Grady Booch? Yeah. You remember that name, because how could you possibly forget that name? It's not like John Smith. Grady Booch. And Grady Booch is the guy who wrote all the big OO books back in the 80s and 90s. He was the guy that was on the top of the mountain and dispensed knowledge about object-oriented design. Ivar Jakobsen partnered with him and with another guy by the name of Jim Rumbaugh to create something that you might be familiar with. It's called the UML, the Unified Modeling Language. And Jakobsen got into that role because he had published this book. That's one of the reasons. Actually, what happened was Rational bought his company for an awful lot of money, and then he went off and bought an island after doing the UML. So that's nice. Jakobsen wrote this book, and the book is a good book. It's called Object-Oriented Software Engineering, a Use Case-Driven Approach. Now, I remember when this book was not out yet, and we were all kind of waiting for it to be out. There had been hints. Oh, yeah, Jakobsen's written the book. Oh, it's got OO in the title. It'll be cool. And so we all waited for it to come out. And then when it came out, I was at a conference when it came out, and the bookseller was bringing brand new copies. So we all lined up, and we all paid lots of money, and we got the Jakobsen book, and we were all very happy, and we were reading it avidly. Talked about this, a use case driven approach. First time anybody heard the word use case. Anybody remember use cases? Use cases. Use cases were instantly popular, overridingly popular. The whole idea became popular, and this happens in software a great deal. There are many things that become far too popular. And then their popularity ruins them because the definition of what they were gets lost. We have a word like that right now. It's agile. We don't know what that is. No one has any idea what agile is, except they know they do it. Use cases were destroyed by the influx of consultants that had to outdo each other. So every consultant would come up with a new PDF. PDF was brand new in those days, so everybody had to put out a PDF of a use case form. And if one guy created a use case form, then the next consultant had to do a better use case form. And the use case forms just got bigger and more elaborate. And the poor people who were trying to do use cases would get these forms that were 9,000 pages long, and you'd have to fill out the title of the use case and the actors of the use case and the preconditions and the postconditions and the primary actor and the secondary actor and the tertiary actor. No one would do it. And everybody forgot what Jakobson had written in his book, which was actually very good. His goal was to say, look, we're going to drive the design and the architecture of our application by looking at what the user wants. And here's how he did it. This is a Jakobsonian use case. I may have put a little too much form on this. His were very, very primitive, and they were meant to be very primitive. Imagine that we have an order entry system. And this is the use case for creating an order. Now, the use case is very simple. There's almost no detail here. That's intentional. We're not supposed to put detail on a use case. What we see here is the incoming data, some kind of customer ID, some kind of shipment destination, payment information, customer contact, and so on. This is the data coming in. Notice that the structure of that data is not defined. I'm not telling you what any of the fields in here are, or what the structure, whether it's ASCII or EBCDIC or binary numbers. I'm not telling you anything. Just that that's the kind of data that we expect. And then there's the primary course. This is what Jakobson called it. We would nowadays call it the procedure. This is what we're going to do in the normal course when this data comes in. And the first step is the order clerk issues the create order command. That's actually not even part of the use case. That's just what kicks the use case off. 2, the system validates all the data. I don't say anything about how. It's not interesting to me right now. 3, the system creates a new order and determines the order ID, probably using a database of some kind, but who cares? That's not what I'm interested in. And 4, the system delivers the order ID to the clerk, probably on a web page, but I don't care to say that right now. In fact, the create order command may have come in on a web page, but that's irrelevant to the use case. The use case is not mentioning the I/O device. The use case is simply saying, hey, I'm going to get this data, I'm going to do this with the data, I'm going to create that output. And the use case is done. Obviously, you would have to get more detail than this, but you would do that later. In 1992, we were beginning to understand, after many, many years of abject failure, that it is not a good idea to define everything up front. It's not a good idea to analyze everything up front and then design everything up front and then hire a bunch of coding monkeys to implement the perfect design that a bunch of people have come up with. It doesn't work very well. And by 1992, when Jakobson wrote his book, it was becoming clear that the act of specification, early specification, was one that was almost devoid of detail. That later on turned into things like user stories. In fact, the use case is the legitimate father of the concept of user stories, because the use cases got so nastily destroyed. Jakobson said, remember the title of his book, Object-Oriented Software Engineering, so this has got to be about OO somehow, right? Jakobson said, this is an object. Use case is an object. You can turn it into an object. He called it a control object. I'm going to call it an interactor because I don't want to confuse you with model view controller. Some people have criticized me for calling it an interactor. They suggest that I call it a use case object. They might have a point there, but it's too late. An interactor object is an object that orchestrates the use case. It has the logic inside it that accepts the input data. It does something with the input data, which I'll tell you in a minute, and then it produces the output data and releases the output data through its interface. That's its job function. I have specified something here. Interactors have application-specific business rules. This word's very important, because every application has two kinds of business rules. There are the business rules that are core to the business problem. And then there are the funny business rules that have to do with the particular application that we're in right now. So, for example, calculating the cost of an order might be an intrinsic business rule, a business rule that applies to many different applications that process orders. On the other hand, the act of creating an order is probably specific to an order entry system. This is an application-specific business rule. The use cases are always application-specific because the use cases are targeted at a single application. But the use cases, with their application-specific business rules, must somehow access the core business rules, those business rules that are not application-specific. Nowadays, we would call these things business objects. Back in 1992, Jakobson called this an entity. It's the same idea. It's a business object. But it does not know what application it lives in. It's application independent. If we had an order entry system and a separate order processing system, the order entity might exist in both, unchanged. But only the order entry system would have a create order use case. That's the difference between these two. So, data comes in through the interactor. Then the interactor orchestrates a dance with the entities. It sends appropriate data out to the entities, which then invoke their application-independent business rules. The interactor gathers data back from the entities, constructs it into output, and sends the output on its way. That output's going to have to go somewhere, and that input's going to have to come from somewhere. And so Jakobson created another object, which he called a boundary object. At first he called it an interface object, but that's obviously confusing. So he later changed it to a boundary object. And I have depicted them here as interfaces, Java-style interfaces. And notice that the interactor, the use case, implements one of them. That's an implements relationship. So this is the input boundary. Data comes in through this input boundary. There are functions declared here that the interactor implements, and the data will come in through this boundary. The data will get played with by the entities. The interactor will construct output and send it out through the output boundary, which, by the way, is another Java-style interface. So something out here must implement it. We'll talk about that in a minute. Now, this is the entire picture of everything we've seen so far. And what we're going to do is we're going to walk through the processing of a use case. Here's the user out here doing whatever. And the user is manipulating the system through this delivery mechanism. This is probably the web, but I don't want to say it's the web. It might be a console interface. It might be a service-oriented architecture. Is anybody doing that? SOA? Or are you doing microservices?
No, this is microservices, yeah.
All right. Whatever the delivery mechanism is, this is the delivery mechanism. Notice this boundary must be the output boundary because the delivery mechanism implements it. This must be the input boundary because the interactor implements it. So the data flow is going to go through this boundary into the interactor, out to the entities, back out through the entities into the interactor, through that boundary back to the delivery mechanism. And I can show you how this works in a series of steps. The user pushes the submit button or does whatever it is, hits return on the console or whatever it is, the delivery mechanism's job at this point is to gather the input that the user has entered and put it into I call it a request model. That request model up there is a data structure. If you're writing in Java, it's a plain old Java object. It doesn't have any inheritance relationships. It does not know where the data came from. It does not derive from any framework class. It is a raw, plain old data structure with public data elements and no methods. It has all the data that was gathered by the delivery mechanism, and the delivery mechanism has put that data in a form that the boundary here can understand. That data then obviously goes right to the interactor through that inheritance relationship, and the interactor inspects it and says, I know what this request is. This is a create order request, and then it controls the dance to the entities. Using the data in the request model, it goes out and it calls lots of methods on the entities, and it does this really complicated thing with if statements and while loops and all kinds of lovely things. And when it's done with that, it reverses the data flow and gathers up all the data that resides in the entities as a result of that process and constructs a new data structure, which I call the result model. The data structure is just a raw data structure, once again, a plain old Java object, public accessible data fields, no methods. Probably, by the way, not even a data structure, probably just an argument list to a function in here, which is a data structure. It gets passed through the boundary, back through the delivery mechanism where it gets presented to the user by some kind of magic. Can you test that interactor without the delivery mechanism? And the answer to that is obviously yes, because all you have to do to test the interactor is create the request model, pass it into the interactor, get the response model back out, and check that the results are in there. And you can do that without the delivery mechanism being present. In fact, you can do it without the delivery mechanism running. Yes? How many of you have tried to write tests on a web-based system only to find that the web server's got to be running? You can't run any tests because the web server's not running. And the processing inside of your business rules requires that the web server be running. I want you to think carefully about how sick that is. My business rules depend upon the web server. Why? Well, the web server provides all kinds of extra tools and facilities, and I need them in order to get my business rules done. This should make you itchy. Yeah? If you're an architect or a designer, it should bother you that the web server has managed to send its little tendrils out and gather you in, and it won't let you test your code independently. If I do this, I can test the use case. I can test the entities. And the web server, if it is a web server, doesn't even have to be turned on. I don't even have to have it on my laptop. The jar files, the libraries for the web server, I don't need them on my laptop. I can test everything from this layer out. Why do I talk about testing? You do test, right? Everybody here test. Doing test-driven development. Let me see hands. Test-driven development. People doing test-driven development. Oh, look at this. All right, so now we are approaching about 50%, although the hands are doing this. Okay. Had I asked that question a few years ago, it would have been about a third of you. And if it was 5 years ago, it would have been about 10% of you. And if it had been 10 years ago, it would have been 1 of you. Or maybe just me. So the word is spreading. People are adopting these disciplines. Test-driven development was foisted upon us, wrong word, wrong term. Test-driven development was made, we were made aware of it in 1999, 16 years ago, 17 years ago. It has taken a decade and a half to infiltrate. That's typical. How long did it take for structured programming to infiltrate. Does anybody remember structured programming? Yeah, some people here don't know what structured programming is, right? Dijkstra, 1968, said, you know, it might not be such a good idea to write all these go-tos. And now we barely have go-tos in our language. What is it? Anybody in the room used a go-to recently? Like within the last month? I don't have my gun with me. You find it's very rare. But go-tos used to be the only way we transferred control. Our early languages did not have structures like while and if then else. Our early languages had go-to. That was it. And so we went to a lot. And then Dijkstra came along and said, you know, there are these reasons why. And he went into great length about what those reasons were. Why this is probably a bad idea. And the war that was fought over that was bloody and awful. Now, we didn't have Facebook in those days, so it wasn't a war of Facebook memes. And it wasn't a war over the internet of, you know, flames on Usenet or Reddit. They were letters to the editor of publications, but they were manifold and multiple, and they were scathing. Dijkstra's a fool. No, Dijkstra's a god. No, you're an idiot. No, you're an idiot. Same thing. Same thing. And then it all settled out. It took a long time. It took it all settled out, and the new languages came out, and new languages came out. And now there are languages that don't even have a keyword. Java doesn't even have a keyword. They reserved it.
Yeah.
They didn't implement it. And that was purposeful. Same thing happens here. We are learning over a long time to adopt testing behavior. How long did it take to adopt objects? When was object-oriented programming invented?
70s, is it?
66. 1966, two guys in Norway wrote a language called Simula 67.
Oh, yeah.
Actually, they cobbled it together from an old Algol source code. And they fiddled with the Algol, and they created this new language that had objects in it. They didn't know what objects were. All they did was take a data structure and move it from the stack to the heap and think, whoa, this is really cool. I didn't know we could do this. And two people of note were Simula programmers, Jarno Strustrup, who went on to invent C++, and Alan Kay, who went on to invent small programming. And from those humble beginnings, we had the object revolution, which really got rolling in the early 80s. By 1988, it was a big rolling steamroller, which was strange because nobody had an object-oriented language. But we were all reading about it. Oh, objects. And then the war was fought. Regular programmers can't do objects. It's too hard. Only academics can do objects. Besides, it's too slow and you can't debug it and all this stuff, all this nonsense. And now we did have an internet. So the flame wars are going back and forth. Now all of our languages are object-oriented languages. And this is how it works. Eventually our languages simply adopt the thing that we were fighting over, and then it becomes a moot point. Eventually, we will very likely have languages that are written to be testable. And test-driven development will be the obvious way to code in those languages. We'll see how that goes. I think that'll be an interesting exercise. In the meantime, what about that? Model view controller. Everybody know what this model thing is, model view controller? MVC? What does it mean? Model view controller. I know. Well, it also means good. Model view controller is one of these things that got way too popular and the popularity destroyed it. So nowadays, your framework is a model view controller framework no matter what's in it. Let me tell you what model view controller was. That's the guy. And I'm going to butcher his name because I don't think anyone outside of the Scandinavian countries can say it. But I believe it is pronounced something on the order of Trygve Rinskaug. I met him. I was in Norway at the Norwegian Developers Conference, and I went up to the speakers lounge, And I was looking for a place to plug in my laptop. So, head down, where the hell is there some place to plug in? And this old guy reaches over and hands me a power strip. And I take the power strip and I look up. It's Trygve cow. And my fingers brushed. I don't wash that hand. Trygve cow invented Model View Controller sometime in the late 70s for the Smalltalk platform. He was working on Smalltalk at the time. And this is Model View Controller here. The idea is very straightforward. There is some object, a model object, which understands business rules and only business rules, and in particular, one business rule, not many. It does not know how the business rule is displayed. That's the job of the view. It does not know how the data for the business rule comes in. That is the job of the controller. The model is completely independent of either the view or the controller. In fact, if you look at the model, you'll note that it does not depend on anything. Those other objects depend on it. The controller's job is to interact with the user somehow. This is the object that would understand how to accept mouse movement and clicks and keystrokes. And it would then interpret those mouse movements, clicks, and keystrokes into method calls on the model, method calls that had business meaning. The view, notice this funny arrow? That's an observer relationship. This is a registered callback. The view would register with the model. And any time the model changed its state, probably because of a controller, then the model would tell any view that it registered to it, hey, I've changed my state. And the view would then interrogate the model and re-represent the model on whatever device it was supposed to be representing on. This might be a screen, this might be a mouse and keyboard, or this might be any other kind of input element and any other kind of output element. That was Model View Controller. And in Smalltalk, Model View Controller was used in the small. There would be a Model View Controller for a text box. There would be a Model View Controller for a checkbox. A group of radio buttons would have a Model View Controller, and each radio button inside would have its own Model View Controller. This stuff was done in the small. Little tiny things had Model View Controllers. This was the way it worked. But like all things in software, it became synonymous with good. And once something becomes synonymous with good, it gets destroyed. Because people believe that what they do is good, no matter what it does, what it is. And so, obviously, what I'm doing is good, therefore it must be a Model View Controller, which is why we got Document View. It's also why we got this. In a web environment nowadays, Model View Controller seems to look something like this. There's the web out here, whatever the web framework is, and the job of the web is to take HTTP requests of some form, URLs and forms and all that gunk, and parse them down to the point where it can invoke a particular controller, and then it hands all of the data that it has gathered from its HTTP request to the controller, and the controller parses that data, and then the parser calls a bunch of business objects in the model's side of things, and then the controller hands its control over to the view, and the view gathers all the data from the business objects and sends it back to the web after converting it to HTML. And the depiction here of a rat's nest is intentional. You probably recognize it. There are a number of things that happen because of this structure. One of them is that the business objects are not well isolated from the controller or the view. It is not uncommon, for example, to find controller-like functions sitting in the business objects. It is also not uncommon to find businessy-like stuff in the controllers. People have a lot of trouble separating that stuff out. Same is true of the views. It is not uncommon to find view-like stuff in the business objects or business object stuff out here in the views. There's no hard boundary line here. There's just the feeling that you ought to separate them, but there's no mechanism to achieve that separation. And with that, I will introduce the concept of a boundary. Not this boundary, that boundary. See that hard double line? That is an architectural boundary. An architect would set a boundary between two elements of the system and then would construct the system so that all dependencies point in one direction across that boundary. Wherever you see one of these double black lines, you will note that all of the arrows cross it in one direction. When I say all the arrows, I mean all the arrows. No matter what source code module lives on this side of the line, those source code modules can point across the boundary in that direction. No source code module on this side of the line, no matter how trivial, can know anything about the stuff on that side of the line. No reference crosses going the wrong direction. This takes a fair bit of discipline and some tools, because it's really easy for somebody over here to call some function over there, and you don't want that to happen. What you're looking at now is the architectural boundary that separates the business rules from the user interface. And I've shown the user interface in this form because I want to walk through the web version of how this works. This picture is drawn at the moment that the interactor has done its job. It has already processed input, it has already controlled the entities, it has already gathered the data and built the response model, and it is now just in the process of passing that response model through the output boundary into, and here we have a new object, the presenter. Some of you have heard of model view presenter. This is just a depiction of that. The job of the presenter is to take this data structure, which is pure data, no dependence on any framework, and to present it into another data structure called the view model. Some of you might be doing .NET, you know about MVVM. This is the kind of view model that you have in MVVM. The job of the view model again is a raw data structure. It has no methods in it, probably. It's just a bunch of public data fields. But the data in the view model is organized for presentation. So, for example, if there are currency objects over here, by the time they get over here, they've been turned to strings with currency characters in them, with the right number of decimal places. If they need to be colored a certain color, then by the time they get to here, there will be a little variable in the view model that depicts the color associated with the field to be displayed. If there are menus that need to be displayed on the screen, there will be a data structure in here with all the menu item names. If there are buttons that need to be on the screen, there will be little data structures in here that tell the names of the buttons. If certain buttons need to be gray, there will be booleans in here that tell you that button should be gray, but that button should not. Same with menu items. No decision is left unmade regarding presentation. The presenter does all of the decision making, loads the data structure with all of the data ready to be presented, and then hands it to the view. Notice that I have drawn the view as this object that barely exists. That's because it barely exists. And there's almost no code in here because all it has to do now is gather the data from that data structure and do whatever very minor thing needs to be done to put it into the actual view. Probably it's going to be putting it into some HTML structure, but all of the translation has been done, all of the textual presentation has been done, all of the formatting has been done up here. There's nothing left for this to do except move the data. Can you test that, presenter? Yeah, you can. You hand it a response model, you examine the view model. You have to have the web server running to test that, presenter? Now, what's left to test? Well, that. But there's no code in there. Probably this you will test with your eyes, because there's no code in there. probably you'll test it with your eyes. And it's really easy to test this with your eyes, because all you have to do to test this with your eyes is to hand it a dummy view model. Fire up the web server with a little shim on it that accepts view models, and just pop a view model in and watch what it presents. I did it right. And if you really want to, you can then scan the HTML and make sure that the HTML came out right, but you probably don't have to do that. At least I don't. Usually when I'm doing GUIs, the very last step I eyeball. There's just not that many eyeball steps left. This is the way that we cross that boundary. And notice all the lines point in one direction. That's significant because if in the Java world, I can put this in a jar file. And I can put that in a completely different jar file. This jar file knows about that one. That jar file doesn't know about this one. Which means I can deploy them independently of each other. You don't have to know about each other. And in fact, I can deploy this jar file with all the business rules in it with a completely different jar file that has a different user interface on it. So if I want to ship it as a console interface, just swap out the user interface jar file. If I want to ship it as an SOA, God help you, then you put some kind of SOA jar file out here. In fact, just to show the whole thing, there's the controller. The controller is the same as it always was. The web will call the controller, but the controller's job now has been constrained to nothing more than creating a request model and deciding which interactor boundary to pass it over. And the job of the presenter is to gather the response model from the interactor and to hand it off to the view as a view model. And once again, notice the hard double line and all the dependencies pointing in one direction. Get used to this idea of hard boundaries with dependencies pointing in one direction. If you're Java programmers, get used to the idea of thinking of separate jar files across that boundary. If you're .NET people, separate DLLs. If you're Ruby people, separate gems. And everybody's got one of these things, so something like that. What about the database? What is a database? What is a database?
IO device.
It's an IO device. It's an IO device. And what are we supposed to do with IO devices? Abstract them. We're not supposed to know they exist. Why do we have databases? Persistence. Well, I could have persistence with a file system. Damn good persistence, too.
Structured.
It's structured. How?
It makes it easier to query. How is it structured?
It's got query. It's got a query language built into it. That's useful, isn't it? It's nice to have a query language. Yeah? That's good.
It supports transactions, for example.
It supports transactions. That's good. We like to have transactions. Why do we like transactions?
You have to let them know you have waste conditions.
Yeah, people tend to update things at the same time, right? And so we have to lock one and then lock the other, and transactions are a nice way to avoid deadly embrace. So, okay, we got to have all that stuff. And that's not why we have databases. We have databases for another reason, at least historically. All those other things became true later. But the reason that we have databases is because we were storing the data on a disk. Has anybody ever written a disk drive? How the heck do you store data on a disk? What's the format of that data? Anybody know how a disk is structured? All right, so you got this round piece of metal that has some magnetic coating on it, right? And you may have many of them, these disks, and there may be many disks stacked up into a pile, right? And then you've got some heads, and the heads can move in and out of this across the surface of the disk. And the heads have little magnetic read-write things, little coils. That's what's really going on there. And what you do is you figure out where you want to put your data. Let's say we're going to read some data off the disk. All right, first of all, you got to know which track it's on. So how far do you send the seek head in? How far do you send those heads in? Then you've got to know which disk it's on, so you need to know which head to read. And then you've got to wait for that disk to come around until the sector with your data on it comes under the read head. And then you've got to read the whole sector, which is usually 4K. And then you put that in a buffer, and then you look inside that buffer to get the byte you want. That's a pain in the ass. And it's slow. I mean, you got mechanical things moving, right? And spinning. It's slow. This is millisecond stuff. Dozens of millisecond stuff, not the nanosecond stuff that we're used to. So you need something to cache it and organize it and somehow conveniently get the data off this horrible medium so that you can use it. That's what a database was for. That's why we had databases. In fact, we had two different kinds of databases. We had file systems and we had relational databases. Relational databases came along a little bit later. Who's got laptops with them? Right now. Got laptops? Who's got laptops? Hmm? How many of them have a spinning disk in it? You're all going to have to take him out and buy him a beer, because that is one sad story. If I had asked that question 2 years ago, there would have been several people in the room that had spinning disks inside their laptop. If I had asked it 5 years ago, there would have been one guy in the room who had an SSD, and he would have been looking at us all going, and we would have hated him. The disks are going away. We don't have disks anymore. Even in the big server farms, the disks are going away. What we have now, and what we will continue to get, is a virtually infinite amount of RAM. And we're still accessing it with disk drivers. God help us. We're still pretending like it's on a rotating medium with sectors. We actually still do the math to calculate where is it going to be on the disk. There's no goddamn disk, but we're still doing it. But bit by bit, we will get rid of all that horrible code, and we will be left with what amounts to an infinite amount of RAM. Infinite, I should not say the word infinite, I should say unbounded. Finite, but unbounded. 64 address spaces, virtually unbounded. Now I want you to think about what you do with the data that comes off of a relational database. When you do your query, you organize and select this and that, and with the left this and the right that, and this, and you get a table. And what do you do with that table? Well, you unpack it, and you put it into binary trees and hash tables and linked lists so that you can operate on it. Because you don't want to deal with tables. Tables are inconvenient. You want pointers. You want all those dumb relationship tables. You want to turn that into pointers and references. You want to be able to index into arrays. You want to get things out of a hash table. That's what we do as programmers. We want it in that form. We don't want it in that table form. Table form is not useful to us particularly well. What if you could just store it as a hash table and a linked list and a binary tree? What if you could just leave it out there in that form? What if you had an infinite amount or indefinite amount, a finite, unbounded amount of persistent RAM? And that's the direction we're going. If I were Oracle, I'd be scared to death right now. Because the reason for my existence is disappearing. That disk, which was why I existed in the first place, is fading away. Got any DBAs in the room? They now hate me. But watch out for this. And if you have an infinite amount, or a finite and unbounded amount of space, how would that change the way you store data? And let's also say that you have a finite but unbounded capability to process that data. Cycles per second is finite but unbounded. How would that change the way you think about processing that data and keeping that data? Right now, we tend to think of data in terms of state. We might have an account, and that account would have a person's name and their address and their phone number and their bank balance. And that account would be a record out on disk. What if instead of that, By the way, that account is subject to transactions, because two people might try to alter it at the same time. What if instead of that, I did not store the account at all? What I stored on my database was the transactions that modified the account. I would store every deposit. I would store every change of address and every change of phone number. And if I wanted to know what the state was, I would just add up all those transactions. And right now you're thinking, yeah, but that's a lot of processing power. We got a finite and unbounded amount of it. Oh, that's a lot of memory. We got a finite and unbounded amount of it. And if you did that, you'd never delete anything. There'd be no such thing as a delete. There would be no such thing as an update. You would never change anything. You know, CRUD, create, read, update, delete, that becomes CUR. You may now create things and read things, but you will never update, you will never delete. And if you don't update and you don't delete, you don't need transactions. Concurrent update disappears. What system do you use every day that works that way? Source code control systems. Your source code control system is a CUR system. You do not delete anything inside there. You do not update anything inside there. All it stores are the deltas, the changes. And then when you check out code, it applies all those deltas. Now, in order to be fast, it does snapshots every once in a while so that it doesn't have to do a complete update from time zero. But that's just in detail. We, programmers, use a system like this. And then, for our customers, we force them into a state world. That's going to change. I told you all of that so I could tell you this. How many of you still today think of your system in terms of that diagram? The great database god in the sky with all the minion applications around serving it. Oh, the database gods, we bow to them. We will provide small applications for your pleasure, sir. Some of you might recognize that attitude. Where do you think that attitude came from? Who benefits from that attitude? The database vendors in the 70s and especially in the 80s did a masterful job of marketing databases, not to programmers, but to executives. And they invented this lovely term, data assets. That sounds really important, doesn't it? You go to an executive. Are you protecting your data assets? God, I didn't know I had any data assets. I have. And our system will protect your data assets. How much does it cost? Millions of dollars. Okay. You need completely separate job functions in order to deal with the system that protects your data assets. We call them DBAs. And they must be the high priests of the system that rule with an iron fist over the schema. They don't allow the minion programmers to touch the structure of the data, and you know the story. This served the database companies very well. That strategy worked really well until lately, when the disk started to disappear and the NoSQL movement started going, and everybody's scratching their head going, why the hell were we doing this in the first place? No one can understand. I want you to dissolve this view in your mind. Think about the database, regardless of all the interesting power it has, the querying power and the reporting power and all that power. I want you to think of it as a detail. It's just an I/O device. So it's got some cool features. You can use them, but it's an I/O device. It is not an architectural element. And because it's an I/O device, we want to separate it from our application using one of those double-lined boundaries again, which we can do by doing something like this. Here we've got our interactor. Our interactor plays with the entities. You might have thought that those entities would have been objects on the database. They're not. Because what's an object? Definition of an object.
Abstraction.
State and behavior. And what about that state? What are you allowed to know about that state from the outside? Nothing. Keep all your data private. You know, you have that private keyword that we use, private. You're not allowed to know anything about that data. The only thing you're allowed to know about an object from the outside are the methods, and only the public methods. Which means that from the outside looking in, an object is nothing but behavior. That behavior can communicate state, but you don't know where that state lives. That state may not be in the object. It might be somewhere else. You have no idea the form of that state or the location of that state. You have no idea, nor should you have any idea. So these objects here are business objects that have business functionality. They probably do use some state, but you're not allowed to know where that state is or what form it's in. The gateway here is a special little interface, and it's the interactor's job to use it. You know that query language that you like inside the database? We're not going to use that up here. No SQL up here, no query language of any kind up here. Any query that you want to do is a method here. And you'll probably have several of these interfaces for the various different entities in your system. If you want to read a particular entity, there'll be a read function here. If you want to get a list of all of the orders that were created after a certain date, there would be a method here. Get all orders after date. Anything you want to do for that persistent data, there's a method here in this interface, which gets implemented down here to use the database. Anybody using Hibernate?
Yep.
Huh. What's Hibernate?
Horrible.
It's not so bad. It's just when it's used in the wrong place, it gets in the way. What is Hibernate? An ORM. What does ORM stand for? What is it?
Object relational.
Object relational mapper, right? There's no such thing as an object relational mapper, right? Because objects are behavior, not state. Relational databases are state, not behavior. There's no way to map that. There's no such thing as an object relational mapper. People have talked for years about the impedance mismatch between relational databases and OO. There is no impedance mismatch. There never has been one. They're completely separate things. State and behavior. What an ORM is, what Hibernate is a data structure hydrator. It goes out to a bunch of tables and it loads a bunch of data structures. And it does so through a set of rules that you define. And it creates a bunch of data structures in memory. Hibernate does not instantiate objects because Hibernate has no idea what the behavior of those objects are. If you took all the methods out, it would still perfectly happy fill in all the data fields because that's all it can do and that's all it should do. Hibernate lives down here, or whatever tool you're using lives down here, not up here. Guys doing Hibernate in Java, who's doing Hibernate in Java? You got those little add auto-wired things? Yeah, none of them up here. No auto-wireds up here. I don't want any of this stuff to know about Hibernate. Right? I don't want anything up here to know about dependency injection. All this stuff is your family jewels. This is the business rules. You don't let frameworks in here. Frameworks. Who writes these frameworks? Hibernate. Who writes that? Do you know them?
I don't know them.
Do they have your best interest in mind? Are they going to take care of you when you inherit from their base classes? Which, of course, they would love you to do. Why does a framework author want you to inherit from their base classes? Because it validates them. When people inherit from my base classes, I know that I have them forever. Because they'll never escape me after that. Once you inherit from a framework's base classes, that framework owns you. but you don't own it. You have no control over the framework author. You don't know what that guy is going to do tomorrow. You don't know what the team that's maintaining it is going to do tomorrow to screw you. Anybody here been screwed by a framework? Yeah. Now, you might think that makes me anti-framework. I am not anti-framework. I think frameworks are lovely things. I think they provide lovely capabilities. You should use them, but you should use them at arm's length. You should put them behind a boundary. You should not let them in here, because these are the family jewels. This is the stuff that makes money for your company or saves money for your company. This is the code that they pay you to write. This is the stuff that's important. Keep the frameworks out of that. Dependency injection frameworks, keep it out of there. Hibernate, web server frameworks, all that stuff, keep it out of here. Use it down here. If you've got a nice little double line boundary somewhere, put the frameworks below in that boundary. Fine. Just keep them out of here. Tell you a little story, and then we're going to be close to done. Long ago, the year was 2001, my son and I began a project. It was called Fitness. Fitness was is a wiki. It was also an acceptance testing tool, one of the early ones, something like Cucumber. Anybody using Cucumber? Or SpecFlow? Or JBehave? Or, yeah, okay, sorry. Maybe you're using this, maybe you're not. But okay, that's one of the tools. This is one of the very early ones. And we set about to implement it in Java. And we said to ourselves, okay, we need this to be a wiki. And wikis have persistent data elements, which are pages. Where are we going to store those pages? Well, obviously, we wanted to store them in a database because that's what you do. You store things in databases. So we said, well, it's an open source project. What open source database was there in 2001? MySQL. That's all there was, MySQL. I said, all right, we'll get MySQL out and we'll do that. What's the schema for this database? What tables are we going to need? We started to go down this pathway of figuring out the entity relationship tables, and somebody said, wait a minute. We don't need to do that right now. Because there's another problem we can solve that has nothing to do with the database. We've got this markup language that needs to be translated into HTML. And that's going to take us a long time to do all that. We're going to parse the markup language and translate it to HTML, make sure it works. We could be doing that for weeks before we need a database. And we thought, that's a good idea. So what we did is we created this object called a wiki page. And it had a whole bunch of methods in it, but the two that are interesting to us is this one, toHTML, which invoked the markup language to HTML process, and the save method, which was dummied out. It was actually more than save. It was read and save and all of the normal kind of database activity you'd expect, except that we stubbed it all out in a page called the mock-wiki page. So wiki page was an abstract base class with a bunch of methods in it, and then the mock-wiki page just mocked out the save and read to do nothing. And for about 3 months, we busied ourselves writing the code that translated the markup language into HTML. And that was great. And we actually got stuff on the screen, and we could see it working, and it was really cool. And then at some point, we were doing test-driven development, so that we finally exhausted all the tests we could write that didn't have some kind of persistence. And then, okay, we got to do persistence. We're going to have to get that database now. And somebody said, well, we don't really have to get the database yet, because what we could do is take and store the pages, which are rather small, into a hash table. And we could access them by a key. And we'll do that through the right methods so that it looks like a database. It's just that they'll actually be in a hash table in RAM. And the complaint there was, yeah, but if you save there's no way to save the data, right? If you shut down the program, you lose all the data. Well, we don't care about that now because we're just doing test-driven development trying to make it work. So we thought, that's not a bad idea. And for a year, we lived in this mode. And we got the whole wiki working. We got the whole test framework working. We got everything. We could do anything that a fitness system except save. And that was fairly inconvenient. But a whole year of working, and we had the whole thing. We could demonstrate it. Took a lot of setup time to demonstrate it because we had to load up a bunch of pages. God, I hope it doesn't crash. Eventually, we ran out of tests that we could write that did not depend on in-RAM persistence. The next test we had to write depended on the fact that there was a page stored in a real persistent database because we were starting to do the boot up sequence. We had to read a bunch of pages with that boot up data on them. So we said, all right, now we've got to get the database running. And Michael Feathers was there at the time. He said, well, you don't really have to get the database running because it wouldn't be very hard to take that hash table and write it out to the file system and just use flat files in the file system. And you were all going, oh God, flat files in the file system. That's awful, but it would work. And he came back the next day with it all working that way. I thought, okay, this is cool. And then we kept on writing tests. And, oh, by the way, now we could demo it. We could take it on the road because we had persistence. And we'd go out on the road and we'd show people, yeah, that's really cool. We'd let them use it in beta because for some reason we allow people to use our betas. Anyway, on and on, months and months go by, always intending to get MySQL until the day came where we all just kind of looked at each other and said, this is good enough, isn't it? We don't need this MySQL thing. And we never did put it in, which is not exactly true. Because a customer of ours came to us a year later. And this customer said, we've got to have it in MySQL. We said, why? It works fine. Flat files are fast enough. Everything seems to work. Why do you need it in MySQL? Well, management says we need to protect our data assets. You can't fight City Hall, so we showed him this structure right there. We said, all right, look, all you're going to have to do is write this class, except call it MySQL page, and rewrite the data access methods. He came back the next day with the whole thing working in MySQL. We used to ship that as a plug-in to Fitness, but no one ever used it, so we don't anymore. Even he stopped using it after a while. The moral of that story is that the things that you think of as architecturally significant elements probably aren't. They can be deferred. And they may be deferred so far that you defer them off the end of the project. And that leads to a conclusion, an interesting one. A good architecture allows major decisions to be delayed, to be deferred. It is not the job of the architect to make major decisions like databases and frameworks and so on. It is the job of the architect to open options, to keep the options open as long as possible so that when those decisions must be made, they can be made with the most amount of data. A good architecture maximizes the number of decisions not made. The job of an architect is to delay as long as possible decisions. Now, you may have some decisions that are forced upon you. You know, we're an Oracle shop. We use Oracle. That's fine. But you can still pretend like you don't know what database you're going to use. And you can defer that dependence upon Oracle for a very, very long time. You might be able to defer it long enough for Oracle to go away. Last slide. The architecture I'm talking about here can be demonstrated with this simple diagram. We have a component with all of our use cases in it. A real system would actually have multiple use case components, but it would still fit into this diagram nicely. Notice the direction of the arrows. The use cases depend upon nothing external. The use cases stand alone. The use cases don't know what the UI is, don't know what the framework, what the database is, don't know what the frameworks are. The use cases are the family jewels. They stand alone, they are protected. It is these guys out here that are vulnerable. What IDE do you use? IntelliJ, good one.
Nobody will say Eclipse because Eclipse is not cool. So
I
use
see.
Eclipse.
All right, don't say Eclipse. We have any .NET people in the room? What IDE are you using? There's so much competition. But if you are using Visual Studio, not Virtual Studio, Visual, because there's nothing virtual about it, Visual Studio. If you are using Visual Studio, I hope you are using ReSharper, or one of the good plugins that make Visual Studio almost usable. Now, ReSharper is a plugin. It looks like that. Here's Visual Studio, bunch of use cases, and here's ReSharper. And the dependency structure looks exactly like that. Right? ReSharper knows about Visual Studio. Visual Studio doesn't know a thing about ReSharper. Doesn't care. Those guys could go away. Visual Studio would still be here. Which of those two development teams could completely screw the other one? Pretty obvious, right? I mean, what can these guys do to them? The answer is nothing. At runtime, they could do some nasty stuff. But at compile time, at source code level, there's nothing these guys can do to their source code that bothers these guys in the slightest. On the other hand, these guys, by carefully manipulating their source code, could drive them out of business. Every week, there's another interface change. Sorry. Oh yeah, we moved those methods into a completely different interface. Yeah, change the calling signature entirely. These guys are vulnerable. They can be harmed by that. This guy is invulnerable, cannot be harmed. And ask yourself, are there things in my application that I want to be invulnerable, that cannot be harmed by the vagaries of things that happen out here, the vagaries of marketing people manipulating user interfaces? You have marketing people that manipulate your user interfaces? Oh, those web pages are just like so 2013. We need to change the whole architecture of the website. If that screws up your use cases, you've got a crappy architecture. Because that change, any change out here, you ought to just kind of whistle and go, okay, no problem. Change the web structure all you want. Change the way the pages are laid out. Change the navigation structure. Change the LDAP server. Change anything you want, because it's not going to touch the business rules. They don't care. I'm not even going to have to recompile them. Use the same jar file. That's where you'd like to be. And with that, I think I will end my talk. Are there any questions? You have one?
Yes.
Okay.
For the slide with the entities, one of them anyway. There you are.
That one?
No.
No. That one? No.
No.
That?
No.
No.
Entities.
Ah.
Let's see. Okay. Well, almost. So.
Almost.
Oh, any of them is
No, that.
The question is, does JQL break any of your rules? Because
Does who?
JQL,
What's JQL?
the query language of JPA.
The What's a TLA? TLA?
Three-letter acronym.
Three-letter acronym. All right, good. Yes.
I used to work in Ericsson. So
Yeah. Okay.
I'm trained in this. Okay, so the query language of JPA, it exists in the entities. Is that wrong?
Oh, what's JPA?
It's an abstraction of Hibernate.
It's an abstraction of Hibernate. Is it a framework?
Kinda.
Yeah.
No.
Yeah.
It's an abstract framework.
It
is a framework.
Is it part of the Java language?
Yeah.
No.
Huh? Oh no, sorry. No.
Part of the Java suite. Right? It's in Java. It's in the Java domain or kingdom or dictatorship or whatever you want to call it. But it is not part of the language. Right?
Yeah.
So I would look at it skeptically. Does anybody remember what came before JPA?
Hibernate?
Hibernate.
Well, that was kind of a separate
EJB2, okay.
EJB2.
Oh, yeah.
And then what was before that?
EJB1?
EJB1. And then you get the idea that they tried? Well, that sucks, let's try again. Well, that sucked too, let's try again. Maybe they'll decide this one sucks. Oh, well, let's try again. Framework authors change their minds. It just happens. So I would take anything like that and keep it outside the barrier, outside the boundary. I don't want anybody that offers me the secret key to using databases, I'm going to be putting on the other side of that boundary. And I know that means that there's a little extra work to do to map all that stuff across the boundary, but believe me, you're going to be very happy you did that. Unless, of course, you're throwing your application away within a month. You know, if you're doing a quick and dirty, month-long thing, doesn't matter. But if you're trying to build something that's going to last a couple of years, keep that stuff separate. Anybody else? Yeah?
Is there a framework you like? And why?
Everybody loves me. I don't dislike any of the frameworks. I distrust them all. But I don't dislike them. I just don't think that they've got my best interests at heart. So as an engineer, I look at anything that I don't have control over with a certain amount of skepticism. I've been doing this for 40 some odd years. I am slightly jaded. I've been burned a few times. So yeah, okay, I'm going to put it on the outside of the fence. And I'll just probably leave it on the outside of the fence, because you never know when that nice dog bites you. So, okay. Anybody else? Yeah?
What's the difference between your interactor and a controller? Or have I missed the point?
So the difference between an interactor and Jakobson's control object is nothing. They're the same thing. The difference between an interactor and a controller, model view controller as defined by the web, can be seen here. Here's the web controller. There's the servlet, or the action, or the object that accepts control from the web server. And his sole role is to organize the data that came in from the URL and the HTTP request into that request model, data structure, and then to determine which of these interfaces to pass that data to. There's probably some factory in here that creates the interactors, and the controller probably knows about that. It probably has enough smarts to say, oh, well, if the URL looks like this, then I really want to create interactor 72, which has this interface. A fair bit of interesting manipulation going on there, some code, but no business rule code. This is all business rule. This is all getting to the business rules. Answer your question? Okay, good. Anybody else? Yep.
What will be the answer to your son about when you saw the structure showing you that it was a language but not a map, a structure
Yes.
system?
So if I went all the way back to that original diagram that gave me the problem, the directory structure that my son had, the question I now have is, where are the use cases? Where's the directory that says use cases? I want to see that. And I don't want to see all of this stuff at the same level. I want to see a use cases directory, and then I want to see a UI directory, and I want to see a database directory with everything underneath that. I want to see all of the framework stuff at the top level. One more. Yeah?
Question you don't have to answer.
Okay, good. You don't have to ask me.
Given that we're in such short supply of programmers, why do you think it is that there are so few women programmers these days?
Okay, well that's a hot button. So first of all, let's go to the first part of that. There is a huge need for programmers. How many programmers were there in 1948? Now, maybe you think that was a long time ago. Right? That was only 66, 67 years ago. So one man's lifetime, almost mine. One person's lifetime. How many programmers were there? One. Alan Turing, one guy. Maybe we should say big O of one, because there was probably a small staff, but there was only one computer. One electronic computer that we would call a computer in which you actually wrote binary code. One. By a year later, there were 4 or 5. By 5 years later, there were a dozen or so. By 1958, there were probably several dozen. 10 years later, 1968, there were thousands. 1978, mini computers had come along. There were tens of thousands, probably hundreds of thousands. By 1988, we had microcomputers. There were millions, probably tens of millions of computers. And we could keep that going. To the point that now, in this room, forget the laptops, forget the iPhones, forget all the smartphones, forget the stuff on your body. In the walls of this room, there are dozens upon dozens of little microcomputers doing all kinds of stuff that we don't even think about anymore. To the extent that a human being in the Western world now interacts with software every single second of their waking life, and probably during their sleep as well. One person's lifetime has seen that level of change. And the number of programmers in the world has followed a similar curve. So it's easy to estimate the growth rate of programmers. And the growth rate of programmers has been stunning. The number of programmers in the world doubles every 5 years. Every 5 years, the population of programmers in the world doubles. And this rate has been maintained for virtually 65 years. It probably can't continue at that rate much longer because we're going to run out of people. On the other hand, it would not surprise me at all if in 15 years the major career category, the major employment category, was information worker. Most people will be information. Even now, it's close to 10%. That number, doubling every 5 years, has a very deep implication. Half the programmers in the world have less than 5 years' experience. And this has always been true and will remain true as long as that curve continues. Half the programmers in the world have less than 5 years' experience, which puts our industry in a state of perpetual inexperience. We do not have enough people who have been in the business for 20 years. Right? Hardly anybody. People wonder, like, this is a young man's game. Where did all the old people go? We're all still here. There aren't very many of us. There never were. The first programmers, besides Alan Turing, were women. And in fact, most programmers from the 1940s and through most of the 50s were women. And there's a reason for that. Hardware was considered masculine. Men worked with iron. Women were clerical. And software was clerical. So, Bletchley Park, when Alan Turing was doing the whole World War II thing, they populated that with a lot of women. One thing, all the men were off fighting, but the other thing was that was considered clerical activity. And when computers started to move into industry and into the military, it was the women who were working in that role. So most of the early work done in software was done by women. Some of that you probably know. There's the COBOL language, which was written by Grace Hopper. It eventually became an admiral in the Navy. What you may not know is that Grace Hopper wrote the very first compiler of anything and coined the term compiler. Right? She's the reason we have the word compiler. Right? Women were extremely prevalent programmers through the late 40s, into the 50s, through the 60s. I got my first job as a programmer in 1969. And when I went to the place, they had a nice little office with people at desks, about 40 or 50 programmers. 12 to 13 of them were women. Maybe a little bit more than that. It was just common to see women sitting there writing code. And they were good at it. And I learned a lot from a number of them. 10 years later, 1978, I worked at a company that had 50, 60 people, 2 women. Something happened in that decade, and I think I know what it was. Well, I have an idea. Prior to 1975-ish, there were no university degrees for computer science. You could not take a computer course at college. Oh, into the early 70s, they started to have some computers at college, but it was always part of an engineering degree. There was no computer science course, and there was no great demand for programmers either. I mean, in the 1960s, nobody knew a programmer, because there were only a few programmers back in those days. Nowadays, there's programmers living in nearly every house around you, but in those days, there weren't. But the first graduates started to come out of university with CS degrees, computer science degrees, right around 1975 into 76, 77. And they were cheap. You didn't have to pay them a lot. Who were all the programmers before that? Who were the companies hiring as programmers when there were no degree programs? How did companies get programmers? And the answer to that is they had to look around at their own employees and say, okay, we've got to program these computers. There's got to be some of our employees who can do this job, and they need to be smart, and they need to have experience. They need to understand our business. They're probably technical people like accountants or good clerks or maybe some engineers, and they would gather from their pool of employees. And these people were in their 30s or 40s as they came into the industry in the 1960s. The 20-somethings did not start getting into software until the mid-70s. So now you've got this cohort of roughly equal men and women, a little more than men than women, but not grossly more, in the 60s. And in comes this flood. And it's a flood of kids coming out of school, and they're all young men. For whatever reason, they're all young men. The women are not taking these courses. I don't know why. And the young men flood the field, and they're cheap. So why wouldn't you hire them? And suddenly there's just this fountain of young men entering the field. I was one of them. I actually beat them by about 4 or 5 years, because I didn't go through the university route. Taught myself how to program a computer. Which, by the way, most programmers, 50% of programmers are self-taught. You may have gone through a CS degree, but that's not where you learned it. Now that might be the source of the problem. It doesn't explain why the problem persists. The statistics are terrifying. 3% of programmers are women today. 3%. No other field has that wild imbalance. Why could that possibly be? What is it that is keeping the women out of this field? Doesn't keep them out of science. Plenty of women in other scientific fields, plenty of women in other engineering fields, not 50-50, but 15%. Why are we at 3? That's a really interesting problem. And I don't know the answer to that last bit. I wish I did. But I do know that it starts in the universities, because it's the young men going through those courses. The young women drop out, and there have been interesting statistics on that. They get in, and then they drop out. What's happening in those classrooms that's causing women to drop out? Don't know. What it effectively means, however, is that we are depriving ourselves of half the population of the world, and also creating an extremely unbalanced testosterone-laden field that we all live in. And I imagine there's a few women in the room here. I imagine you live in a world of perpetual discomfort. The same kind of discomfort I would exist in if I were the one man working in a sea of women. I don't know if I could do that. Because, well, I'm not going there. And that was the last question. Thank you all very much.
thank everybody for coming tonight, and thanks so much for Bob for coming down for Tralee and working us into your schedule, and it's a real honour to have you here, and I'm sure you've been such a huge influence on everybody here, our careers and everything, so thanks again, and thanks for coming in.